Okay, so we're going to find out if the series converges or diverges. We're going to do it by using the limit comparison test. So we can use the limit comparison test whenever all the terms are not negative. They're never going to be negative. There's no negative thing in there. And with the limit comparison test, we take the limit as n approaches infinity of the thing we're comparing it to in the denominator, and then our original thing over here. So, and then when we take the limit, if this is not equal 0 or infinity, then whatever applies to b sub n applies to a sub n. So if b sub n converges, that's also going to converge. If this diverges, that also diverges. Unless it equals 0 or infinity, then it doesn't apply that this is the same, this behavior is the same as that. So what is going to be our comparison? Well, we tend to just have something which is the simple, like removing all the nonsense from that. So if we remove all the nonsense, we just have n, and we have n squared squared. So we would have 1 over n cubed. 1 over n cubed. Because this is just, you remove this constant first of all, then you remove the 2, that would give you n, and that would, and then here you would have, and you forget the 1, and you have n squared squared, which is n to the 4th, and this cancels out to 1 over n cubed. So you could do that with comparison because you're just looking at the general trend, like what's it really doing? So without the specifics. Okay, so with this one, we're not looking to see if that one's greater or if it's less than. That's just a normal comparison test. With this one, we take the limit as n approaches infinity. So b sub n is 1 over n cubed, and a sub n is 5 plus 2n over 1 plus, that doesn't look like a plus n squared squared. Now we can multiply by the reciprocal when we divide. So this would be 5n cubed plus 2n to the 4th over 1 plus n squared all squared. Taking the limit as n approaches infinity. Okay, so now we have an n to the 4 and we have an n to the 4, so we tend to divide by that. We divide by that when we take the limit like this. That's what we do. We look at the greatest one, and that's similar on both, and we divide by that. So limit as n approaches infinity. So this would be 5 n cubed. We already know that that's going to go away, and the n cubed is going to be there. We're dividing by n to the 4. So this would be plus 2. And over here, we would get 1 over n squared plus 1 squared. Once we divide by n to the power of 4. Okay, so now we can take this limit. We could take this limit. So this would go to 0. We plug in infinity, that goes to 0. And this goes to 0. So we are left with 2, which is not 0 or infinity. So whatever happens to this one also happens to this one. That's what we wanted. So what does happen to that one? Well, it's a p series. It's 1 over n to the 3, to the power of 3. Our p is 3. P equals 3. Remember with our p series, when p is greater than 1, what happens? When p is greater than 1, it converges. The way you remember that is because the denominator is getting very large, so your term as a whole is getting very small, and smallness indicates convergence. So p is greater than 1, converges. P is less than 1, less than or equal to 1, diverges. In our case, our p is 3, so this is going to converge. And because this equals 2, which is not 0 or infinity, whatever happens to this guy also happens to this guy. So if this guy converges, this guy also converges. So we have prove that this converges.